Today we are going to solve one more problem from JEST 2021, so part B, question number 10. And so basically from oscillation. So that question is given that you have a cubical box having large volume, that is V. And this box is basically fitted by glass tube having cross-sectional area A. So if I draw that picture, you have a cubical box. And the volume of this cubical box is given, that is V. Okay. And this box is fitted with glass tube. Obviously, there will be hole here. Okay. And the cross-sectional area of this glass tube is given, that is A. And there's a metallic ball is fitted inside this glass tube. Okay. And the mass of this metallic ball is M. Okay. And inside this cubical box, there is an ideal gas. This box contains ideal gas. The pressure inside box is given, that is higher than the atmospheric pressure. Pressure P. Okay. Now, if you displace this metallic ball, there will be oscillation of this ball. So you have to calculate that angular frequency of oscillation will be how much, that you have to calculate. Okay. It's given that that process will be adiabatic, and also is mentioned that ratio of heat capacity gamma is Cp by Cv. So you have to calculate that angular frequency of oscillation when you displace this metallic ball by small amount. So there will be oscillation. Okay. Okay. So as you have seen that this ball, this box, you have a box that is basically inside this box you have an ideal gas, and that is exerting pressure outwards of the center of this box. Okay. And this pressure is actually maintaining two pressure. One is atmospheric pressure P, another pressure is acting towards center, that is due to the mass of this ball. So this pressure due to ideal gas inside box that is acting outward of the center, that is actually maintaining two pressure. One is pressure due to the atmospheric pressure, and the pressure due to the mass of this ball. So I can write that pressure or initial pressure, better, initial pressure P1, that I can write, that will be the atmospheric pressure, and another pressure due to the mass of this ball, and that pressure I can write F. Pressure is nothing but force per unit area, and that force will be the gravity force here, and that I can write like you have a weight mg by A, where the A is the mass of this metallic ball. And of course that initial volume will be how much? Initial volume, that will be V1, and I can write that will be V. Okay. Initial volume V1 will be V. Now, when we'll displace this ball by amount X, there will be change in volume. There will be decrease in volume. So if you displace this ball by an amount X, that final volume I can write that will be V2 and that will be V minus delta V, where delta V will be how much? Delta V will be area, cross-sectional area into displacement, and that I can write A into displacement x. So this means that V2 will be V minus A into x. Okay. So as the process is adiabatic, so when there is a decrement in the volume, there will be increases in the pressure, and I can write that pressure. I can write that pressure or final pressure, that will be how much? That will be P2. I can denote like this, and that will be higher than that. So you have an initial pressure P on, and there is a decrement in the volume. That process is adiabatic, so there will be obviously increment of pressure. That will be delta. Now I'll apply that adiabatic condition because the process is happening adiabatic process here. So I can correlate like PV in adiabatic process. We know PV power gamma is constant in adiabatic process. So it means initial pressure P on V1 की power gamma, that should be same as final pressure P2 V2 की power gamma. Okay. And P2 I can represent like P on plus delta P. And V1 I can represent like you have a V minus delta V की power gamma. Okay. Now if I take delta P common here, we'll have delta P. So on plus P on by delta P. And then you'll have, if you take sorry, if I take P on common here, you'll have on plus delta P by P on. Delta P by P on. Okay. And if I take, I'll write here better, you'll have P on V1 की power gamma. I'll take P on common. So you'll have on plus delta P by P on. Okay. And then you have, if you take again V common, so it will be basically V की power gamma. V की power gamma, and you'll have on plus minus delta V by V की power gamma. Okay, so P on and V on is nothing but V. If you remember, we have seen that. So I can cancel this actually. So we'll have on equals to on plus delta P by P on. And then you have, now we can see if, from binomial expansion, this value is small because V is very large. And in a displacement that is small amount. So if I apply that law, like you have a on plus x to the power n, when x is very, very small, this quantity is actually very, very small. I can write here plus minus, that doesn't matter. I can write like you have on minus nx or plus nx when that x is small. So here you have a x like this, and this very, very smaller than on, very, very smaller than on. So I can write like this. You have on minus gamma delta V by V. Okay, and then if we just multiply, you'll have on plus delta P by P on. Then minus gamma delta V by V, and then you have on by P on V gamma delta P and delta V. Okay, so this on will be cancelled, and you have a delta P. This is also very small quantity, and delta V. This is also very small quantity. So when you have a very small quantity, two quantities, if you multiply that, it will be more smaller, and that tends to 0. So I can basically ignore this term here. So basically it means I can write you have a delta P by P1 and that will be gamma delta V by V1. Okay, so it means delta P will be gamma P1 by V1 into delta V. And delta V, that is nothing but A dx, sorry, A into X, Okay, so when you will displace this ball, there's a harmonic oscillation. So restoring force will be how much? The restoring force will be restoring force so force I can write like you have a as you have seen that pressure is nothing but force per unit area. So it means force will be nothing but pressure into area, and here that restoring force that is arising because of excess pressure, that is delta P. So I can write that restoring force F equals to that excess pressure, that is delta P into area. Okay, and that if we substitute that pressure delta P, and that will be you have a gamma P1 by V1. V1 is how much? V1 is nothing but V. Gamma P1 by V, and you have a square. Now this force, restoring force, if you displace this ball in the downward, that restoring force will act in the opposite direction of displacement. So basically that force direction I can write to make the direction opposite of displacement, I'll write like this. Okay, and this force is nothing but mass of that ball into acceleration, right? Now I can bring this mass here. So I have acceleration that will be gamma P1 by mv. So you have a square here. You have a square here because a already have you have a in the delta P, and you have another a here. So that will be a square. So this is the that equation of simple harmonic motion, and that is nothing but I can correlate like omega square into x. So omega will be how much? That will be gamma P1 into a square by mv. And P1 is how much? P1 I know that is nothing but P plus mg by a. P plus mg by a. So you'll have angular frequency of oscillation of this ball, that will be gamma a square by mv. P is atmospheric pressure plus mg. M is the mass of this ball. A is the cross sectional area of this tube. So this will be the angular frequency when you displace this metallic ball by a small amount. Okay. So this will be the answer, angular frequency, that will be the answer.